Right now, as you're watching this video, something ancient beyond imagination is racing away from our solar system at speeds that would circle Earth in less than 20 minutes. This object has travelled through the cosmic void for longer than our Sun has existed, carrying secrets from a star system we may never identify. And just weeks ago, China's Tianwen-1 Mars orbiter managed to capture the closest images humanity will ever obtain of this mysterious visitor. This is the story of 3I Atlas, an interstellar comet that has left astronomers questioning everything they thought they knew about objects from beyond our solar system. Because what should have been a routine observation has turned into one of the most puzzling astronomical mysteries of our time, and the more data we collect, the more questions emerge about what exactly passed through our neighbourhood. Let me start with something that will give you perspective on just how remarkable this moment is. In all of human history, we have confirmed the existence of exactly 3 objects that originated from other star systems and wandered into ours. 3. Out of the millions of asteroids and comets we've catalogued over centuries of observation, only 3 have made that incredible journey across the interstellar void to reach us. The first was Oumuamua back in 2017, a bizarre elongated object that sparked its own controversy about whether it might be artificial. The second was Comet Borisov in 2019, which behaved more like what astronomers expected from an interstellar visitor. And now we have 3I Atlas, discovered on July 1st, 2025 by the Atlas Survey Telescope in Chile. But here's what makes this discovery different from its predecessors. We've had time, real time to study this object as it approached our Sun, time to point our most advanced instruments at it, time to gather data that was impossible to obtain from the previous 2 visitors. Oumuamua was already leaving the solar system by the time we realized what it was. Borisov gave us a better opportunity, but 3I Atlas has provided something unprecedented. A front row seat to watch an object from another star system perform in ways that challenge our fundamental understanding of how comets should behave. The numbers alone are staggering. This thing measures approximately 5.6 kilometers across, roughly the width of Manhattan from river to river. But unlike Manhattan, this object has been travelling through space for an estimated time frame that predates our entire solar system. While our Sun was still condensing from a cloud of gas and dust 4.6 billion years ago, 3I Atlas was already ancient, already wandering the galaxy as a fully formed relic from an even earlier era of cosmic history. And it's moving fast. Current measurements show it travelling at 58 kilometers per second relative to our Sun. That translates to roughly 129,000 miles per hour. At that velocity, you could travel from New York to Los Angeles in about 2.5 minutes. This isn't the leisurely drift of objects bound to our solar system. This is the velocity of something that has been accelerated by forces we can only theorize about, ejected from its birth system, with enough energy to traverse the emptiness between stars for millions upon millions of years. Now here's where the story takes its first unexpected turn. When astronomers initially spotted 3I Atlas in July 2025, they classified it as an asteroid, just another chunk of rock and ice drifting through space. But as weeks passed and more telescopes focused on this distant speck of light, they began detecting signs of activity. A faint coma started forming around the nucleus, that characteristic fuzzy halo that indicates a comet is warming up and beginning to release gas and dust into space. This wasn't a dead rock after all. This was a comet, an active one, releasing material as it approached our Sun. But even that classification would prove problematic as more data accumulated, because 3I Atlas wasn't behaving like comets are supposed to behave. Its brightness patterns were unusual. Its chemical composition showed signatures that didn't match any comet in our existing database. Most puzzling of all, it seemed to be active at distances where typical comets remain dormant, as if some internal process was driving its behaviour rather than simple solar heating. The breakthrough moment came in early October when China's Tianwen-1 probe, orbiting Mars as part of China's first independent interplanetary mission, turned its high-resolution camera toward this interstellar visitor. The challenge was immense. Picture trying to photograph a city-sized object from a distance of 18 million miles, while that object is moving at speeds faster than anything natural in our solar system. The camera aboard Tianwen-1 was designed to image the Martian surface from close orbit, not to track distant moving targets across the cosmic background. Yet somehow, the Chinese National Space Administration pulled it off, On November 5th, 2025, they released the images, and what they showed was both fascinating and deeply puzzling. Black and white frames revealed a compact, fuzzy sphere surrounded by a diffuse cloud, extending several thousand kilometers in all directions. The coma, as astronomers call this cloud of gas and dust, was clearly visible and active. But something was missing. Something that should have been there based on everything we know about comet physics. To understand why these images are so significant, you need to know what happens when a comet passes close to the Sun. As the comet heats up, frozen materials locked in ice for eons suddenly vaporize. Water ice becomes water vapor. Carbon dioxide ice becomes gas. Other volatile compounds join this expanding cloud of material. The solar wind and radiation pressure from our star then push this material away from the comet, creating the iconic tail that streams behind it, pointing away from the Sun like a cosmic windsock. The closer a comet gets to the Sun, the more dramatic this process becomes. More heat means more vaporization, more gas and dust being ejected, more spectacular tails stretching across millions of kilometers of space. It's one of the most reliable and well-understood processes in astronomy. Thousands of comets have been observed following this exact pattern over centuries of study. 3I Atlas reached its closest point to the Sun, called perihelion, on October 30th, 2025. At that moment, it was approximately 0.9 astronomical units from our star, closer than Earth's average distance, closer than Venus at certain points in its orbit. At that proximity, the heating should have been intense, the outgassing should have been violent, the tail formation should have been spectacular. And here's where the mystery deepens. NASA's Jet Propulsion Laboratory detected something definitive in their trajectory calculations. They measured what astronomers call non-gravitational acceleration. This means the comet was being pushed by forces other than gravity, specifically by the pressure of gas and dust being ejected from its surface. The mathematics are precise and unambiguous. To produce the level of acceleration they measured, 3I Atlas must have lost at least 13% of its total mass during its close encounter with the Sun. Think about what that means. For an object estimated to weigh approximately 30 billion tons, we're talking about 4 billion tons of material ejected into space in a matter of days. 4 billion tons of gas and dust should create a display visible across the solar system, a massive, brilliant tail stretching millions of kilometers behind the comet, debris fields that would be detectable by any telescope pointed in its direction. So, where is it? The images from Tianwen-1, captured just days after perihelion, show a compact coma and absolutely no obvious tail. Ground-based observatories in Italy and Spain photographed the comet during the same period and confirmed the same puzzling observation. A small fuzzy sphere with no clear tail structure pointing away from the Sun. No streaming debris field. No evidence of the massive material ejection that the physics calculations prove must have occurred. Compare this to any normal comet at similar distance and activity level. Just 2 days before the 3I Atlas images were taken, the same Spanish observatory photographed Comet Leonard, a regular solar system comet. Leonard displayed exactly what you'd expect. A clear, well-defined tail pointing precisely away from the Sun, visible across a substantial portion of the sky. It looked like what a comet should look like after losing significant mass near the Sun. 3I Atlas does not look like that. It looks like something that should not exist according to our current understanding of comet physics. An object that can lose 4 billion tons of material without creating a visible tail. An object that can experience massive outgassing without leaving obvious traces of that process. Now, before we venture into more speculative territory, let's acknowledge that there could be conventional explanations for what we're observing. Perhaps the ejected material was primarily gas rather than dust, making it harder to see in optical wavelengths. Perhaps our viewing angle is creating an illusion where we're looking at the tail edge on rather than from the side. Perhaps the mass loss calculations contain errors we haven't identified yet. These are reasonable hypotheses that scientists are actively investigating. But here's what makes this situation particularly intriguing. The missing tail is just one of multiple anomalies that 3I Atlas has displayed since its discovery. Each individual anomaly might have a conventional explanation, but when you start finding multiple unexplained behaviors in the same object, the statistical probabilities become much more interesting. The trajectory alone raised eyebrows among astronomers. When 3I Atlas was first detected, calculations showed it was travelling through our solar system aligned with the ecliptic plane to within just 5 degrees. The ecliptic plane is the flat disk where all our planets orbit, formed from the original spinning disk of material that created our solar system 4.6 billion years ago. But 3I Atlas didn't form here. It came from interstellar space, where there is no preferred direction, no cosmic flat plane that objects naturally follow. Interstellar visitors should arrive from random directions, from any angle relative to our solar system's orientation. Yet this one arrived aligned almost perfectly with our planetary disk, travelling in a retrograde direction opposite to how our planets move, but doing so within the same geometric plane. The probability of this happening by pure chance, approximately 0.2%, 1 in 500. Before we even got to study its composition or behaviour in detail, its arrival path was already statistically unusual. Then came the observations that really caught attention. During July and August of 2025, multiple observatories documented something that shouldn't exist according to conventional physics. 3I Atlas was ejecting material toward the Sun, not away from it. This defies everything we know about how solar radiation pressure and the solar wind interact with comet material. Think of it like trying to blow smoke directly into a powerful fan. The fan pushes everything away from it, not toward it. Similarly, the Sun's radiation should push all comet material outward, away from our star. Yet 3I Atlas was displaying what appeared to be a jet of material streaming sunward, against all the forces that should have prevented such a phenomenon. Multiple research teams analysed the viewing geometry, checked their calculations, and confirmed this wasn't an optical illusion or misidentification. This was actual material being ejected toward the Sun in direct violation of accepted comet physics. No natural mechanism adequately explains this behaviour. As we continue to analyse the data from 3I Atlas, each new piece of information seems to deepen the mystery rather than resolve it. The chemical composition shows unusual ratios of elements. The brightness variations don't match standard comet rotation models. The structural integrity suggests something far more robust than typical comet nuclei. And now, with the Tianwen-1 images providing our closest look at this enigmatic visitor, we're faced with perhaps the most puzzling observation yet. An object that physics tells us ejected 4 billion tons of material, but which shows no visible evidence of that massive loss. What exactly did China's Mars orbiter capture in those black and white frames? What are we really looking at when we study this ancient wanderer from beyond our solar system? And why does every new observation seem to raise more questions than it answers? The data is real, the measurements are verified, the images are authentic. But the story they tell challenges fundamental assumptions about how objects from other star systems should behave when they visit our cosmic neighbourhood. The implications of what we're seeing go far beyond a single anomalous comet. Because 3I Atlas isn't just breaking one rule of comet physics, it's systematically violating multiple established principles, each violation statistically unlikely on its own, all occurring simultaneously in the same object. Let's examine the mass and velocity combination that makes this visitor so extraordinary. At approximately 30 billion tons, 3I Atlas is roughly 1 million times more massive than Oumuamua, our first confirmed interstellar visitor. It's also 1,000 times heavier than Comet Borisov, the second interstellar object we detected. Yet despite this enormous mass, it's moving faster through our solar system than either of its predecessors. In the realm of interstellar space, this combination defies statistical expectations. Larger objects are naturally rarer than smaller debris, simply because there's more small material than large chunks floating between the stars. Similarly, fast-moving objects are less common than slow ones because ejecting something at high velocity from a star system requires tremendous energy, usually from violent gravitational interactions or stellar catastrophes. The probability models that astronomers use to predict interstellar object characteristics suggest that finding something both exceptionally massive and exceptionally fast should occur less than once in 1,000 observations. Yet here we are, with only our third confirmed interstellar visitor, and it happens to be both the largest and fastest we've encountered. But the statistical anomalies don't stop there. When we examine the timing and trajectory of 3I Atlas's passage through our solar system, another pattern emerges that makes astronomers uncomfortable. This object didn't just randomly drift through our neighbourhood. It followed a path that brought it close to multiple planets at precisely the moments when our spacecraft were in optimal position to observe it. In September, 3i Atlas passed within tens of millions of kilometres of Mars, exactly when the European Space Agency's orbiters were operational and positioned for detailed observation. Then it swung past Venus before continuing toward its close encounter with the Sun. Each planetary approach was close enough for meaningful scientific study, but not so close as to significantly alter the comet's trajectory through gravitational interactions. Most remarkably, the timing was calibrated so that at perihelion, when the comet was closest to the Sun, and potentially at its brightest, it was completely hidden from Earth-based observation. The Sun sat directly between us and 3i Atlas during its most critical phase, making ground-based telescopic study impossible during the very moment when the most dramatic activity should have been occurring. It's as if someone had planned a grand tour of our solar system's major observation platforms, while carefully avoiding direct visibility from the planet with the most telescopes and the largest community of amateur astronomers. The mathematical probability of this timing occurring by pure chance falls below 0.005%. Then there's the chemical signature that has spectroscopists scratching their heads. When light from 3i Atlas passes through spectrometers, it reveals the presence of elements in ratios that don't match any known comet composition. Most striking is the nickel content, which appears in concentrations far exceeding what should be possible in a natural comet. In typical comets, when metals are detected at all, iron dominates the spectrum. The ratio of nickel to iron follows well-established patterns observed across thousands of comet studies spanning decades of research. But 3i Atlas displays the opposite relationship, with nickel concentrations exceeding iron by significant margins. This ratio is characteristic of industrially produced nickel alloys, not natural cosmic ice formations. Even more puzzling, the proportion of nickel relative to other compounds like cyanide is orders of magnitude higher than any previously studied comet, including Borisov, our only other interstellar comet for comparison. When astronomers say orders of magnitude, they mean factors of 10, 100, or even 1,000-fold differences. This isn't a slight variation in composition. This represents a completely different class of object masquerading as a comet. Perhaps most fundamentally challenging to our understanding is the water content, or rather, the lack of it. Comets are supposed to be dirty snowballs, composed primarily of water ice mixed with dust and other frozen volatiles. Water typically accounts for 70 to 80% of a comet's mass, and when these objects approach the Sun, that water ice vaporizes to create the characteristic coma and tail we associate with comet activity. 3i Atlas contains approximately 4% water by mass. 4%. That's not a comet by any traditional definition. That's barely ice at all. It's more accurately described as a rock with a slight frost coating. No known formation mechanism in any stellar system should produce comet-sized objects with such dramatically low water content. Yet 3i Atlas is undeniably active, releasing material and displaying comet-like behavior despite having almost no water to vaporize. Something else is driving its activity, some process that doesn't require the water ice sublimation that powers every other comet we've studied. The polarization data adds another layer to this puzzle. When light reflects off any surface, it becomes polarized, meaning the light waves align in specific directions depending on the properties of the reflecting material. Scientists have built comprehensive models of how light should behave when bouncing off comet dust based on thousands of observations over decades. 3i Atlas shows extreme negative polarization that falls completely outside the established database of comet observations. The light reflecting from its surface is polarized in ways that don't match any known natural dust grain models. It's as if the material comprising this object has optical properties unlike anything we've encountered in natural space debris. Every measurement we take, every spectrum we analyze, every photograph we capture seems to reveal another way in which 3i Atlas refuses to behave like the comet it appears to be. The accumulating anomalies create a statistical profile that becomes increasingly difficult to explain through conventional means. But there's one more aspect of this mystery that deserves attention, something that connects 3i Atlas to one of the most famous unsolved puzzles in the search for extraterrestrial intelligence. In 1977, a radio telescope at Ohio State University detected a powerful narrowband signal from space that lasted exactly 72 seconds. The signal was far stronger than background noise and appear to originate from the direction of the constellation Sagittarius. The astronomer reviewing the data was so surprised by the detection that he circled it on the printout and wrote, "Wow," in the margin. The signal never repeated, and its source has never been identified or explained. For nearly 5 decades, the WOW signal has remained one of the most intriguing potential indicators of artificial origin ever detected by our radio telescopes. 3I Atlas arrived from a direction in the sky that aligns with the WOW signal's source location to within 9 degrees. 9 degrees represents a relatively small patch of sky, roughly 18 times the apparent width of the full moon. While the WOW signal's exact coordinates were never precisely determined, and 9 degrees still encompasses a fairly large celestial area, the probability of this alignment occurring by random chance is approximately 0.6%. Is this meaningful? Perhaps not. Coincidences do occur, and the uncertainty in both the WOW signal's location and 3I Atlas's precise origin point makes any connection speculative at best. But when added to the growing list of statistical improbabilities surrounding this object, it becomes another data point in a pattern that's becoming increasingly difficult to dismiss as mere chance. Near perihelion, as 3I Atlas experienced its closest encounter with solar heating, something unprecedented occurred in the observational record. The comet brightened faster than any object in the comprehensive database of comet studies. Not marginally faster, but dramatically, exponentially faster than existing models predicted possible through natural outgassing processes. Simultaneously with this rapid brightening, 3I Atlas began displaying a distinctly blue coloration, appearing bluer than the Sun itself. Normal comets reflect sunlight, and therefore appear roughly the same color as our star, perhaps slightly reddish due to dust scattering effects. Blue comets are extraordinarily rare because there's no common physical mechanism that preferentially scatters blue light more efficiently than red light in typical comet dust compositions. Whatever was causing 3I Atlas to brighten so rapidly was also producing an unusual spectral signature that suggested processes far removed from standard comet physics. The combination of explosive brightening and anomalous coloration occurring simultaneously represents yet another violation of established patterns. And this brings us back to the central mystery captured in those grainy images from China's Tianwen-1 orbiter. An object that mathematics proves ejected 4 billion tons of material, yet shows no visible evidence of that massive loss. An ancient wanderer from another star system that systematically violates every expectation we have about how such objects should behave. 10 separate anomalies, each individually unlikely, all present in the same object. When statisticians multiply probabilities, when they calculate the chances of all these unlikely events occurring together in a single comet, the numbers become vanishingly small. Less than 1 in 10,000, possibly less than 1 in 100,000, depending on which models you apply. At what point does a series of anomalies stop being coincidental and start suggesting something more fundamental about the nature of what we're observing? At what point do we acknowledge that our models might be incomplete, that our assumptions about interstellar objects might need revision? These aren't comfortable questions for the scientific community. They challenge established frameworks and force consideration of possibilities that seem to belong more in science fiction than peer-reviewed journals. But the data doesn't care about our comfort levels. The measurements don't adjust themselves to fit our expectations. 3I Atlas is what it is, regardless of how that reality aligns with our theories about what interstellar objects should look like or how they should behave, and what it is, based on every instrument we've pointed at it and every calculation we've performed, is something genuinely unprecedented in the annals of astronomy. The images from Tianwen-1 will be studied for decades. Those black and white frames captured from 18 million miles away represent the closest look humanity will ever get at this mysterious visitor. Future researchers will enhance them, analyze them with techniques we haven't yet developed, compare them to databases of hundreds of additional interstellar objects that haven't been discovered yet. But right now, in this moment, we're left with questions that challenge fundamental assumptions about what travels between the stars and what happens when those ancient wanderers visit our solar system. The questions multiply when you examine how 3I Atlas has challenged every prediction scientists made about its behavior after perihelion. Remember, this object lost 13% of its mass in a matter of days. That represents the most violent outgassing event ever documented in an interstellar visitor. The energy required to eject 4 billion tons of material should have left visible scars across the comet's structure. Yet when 3I Atlas emerged from behind the Sun in early November, telescopes revealed something that defied all expectations. The object appeared structurally intact. No fragmentation, no obvious surface changes, no debris field trailing behind it. For comparison, most comets that experience even minor outbursts show clear signs of damage. Cracks appear on their surfaces, chunks break away. The nucleus often splits into multiple fragments that separate over time. 3I Atlas showed none of these effects. It emerged from its solar encounter looking remarkably similar to how it appeared going in, just without the 4 billion tons of material that mathematics proves it must have lost. Where did that mass go? How does an object eject such enormous quantities of material without visible consequences? The structural integrity suggests something far more robust than typical comet compositions allow. Most comet nuclei are described as loosely bound rubble piles, collections of ice and rock held together by weak gravitational forces and frozen volatiles. When heated, they tend to fall apart relatively easily. The fact that 3I Atlas maintained its cohesion through such massive material loss implies internal strength characteristics that don't match our understanding of how comets form or evolve. But there's another aspect of this mystery that becomes apparent when you examine the comet's rotation and brightness variations. Throughout its approach to the Sun, 3I Atlas displayed brightness changes that didn't follow the patterns expected from a uniformly rotating irregular object. Most comets show predictable brightness cycles as they tumble through space, with different sides of their irregular shapes reflecting varying amounts of sunlight toward Earth. 3I Atlas exhibited brightness variations that seemed almost too regular, too controlled. The changes occurred with a precision that suggested either an unusually symmetric shape or rotational characteristics that don't match typical tumbling behavior. Some observers noted that the brightness spikes seemed to correlate with specific orientations, as if particular surfaces or features were being presented toward Earth at calculated intervals. This controlled rotation becomes even more intriguing when combined with the trajectory data. Remember, 3I Atlas didn't just pass through our solar system randomly, it followed a path that maximized observational opportunities while minimizing direct visibility from Earth during the most critical phases. The precision of this routing suggests either extraordinary coincidence or something approaching intentional navigation. Consider the logistics of what we observed. An object arrives from interstellar space, aligns itself with our planetary plane despite having no natural reason to do so, passes close to Mars precisely when multiple spacecraft are positioned for optimal observation, continues past Venus at distances perfect for spectroscopic analysis, approaches the Sun at an angle that allows space-based coronagraphs to monitor its activity, and then emerges from perihelion structurally intact despite losing massive amounts of material. Each element of this sequence might be explainable individually through natural processes and statistical coincidence, but when you examine the complete timeline, the precision becomes unsettling. It reads less like random cosmic mechanics and more like a carefully orchestrated demonstration designed to showcase specific capabilities while maintaining plausible natural explanations for each observed phenomenon. The Chinese National Space Administration's decision to attempt imaging 3I Atlas with Tianwen-1 represents one of the most technically challenging photographic achievements in space exploration history. The probe's high-resolution camera was never designed for this type of observation, imaging a city-sized object from 18 million miles away while that object moves at interstellar velocities required complete recalibration of the spacecraft's pointing systems and exposure protocols. What makes this accomplishment even more remarkable is that the Chinese team didn't announce their intention to attempt these images until after they had succeeded. Most space agencies would have publicized such an ambitious undertaking in advance, using the technical challenge as a demonstration of their capabilities regardless of the outcome. Instead, China worked in complete secrecy, only revealing the images after confirming they had captured usable data. The images themselves, while historically significant, raise as many questions as they answer. The black and white frames show a clearly defined coma extending several thousand kilometers from the central nucleus. The structure appears organized, almost geometric in its symmetry. Most natural comets display irregular, chaotic coma formations that reflect the random distribution of active regions on their surfaces. The coma of 3I Atlas shows patterns that suggest more uniform material distribution or activity. The edges are surprisingly well defined for a gas and dust cloud that should be expanding and dispersing according to solar-wind interactions. It's as if something is containing or directing the outflow in ways that natural physics doesn't easily explain. Enhancement of the original images using advanced processing techniques has revealed additional details that weren't immediately apparent in the raw data. There appear to be structures within the coma that maintain their positions relative to the nucleus, despite the continuous expansion of material outward. These formations suggest either extremely dense concentrations of particles or organized patterns that shouldn't persist in the chaotic environment surrounding an active comet. Spectroscopic analysis of the coma material during this period revealed another anomaly that has puzzled researchers. The gas composition showed ratios of carbon compounds that don't match any known formation environment. Carbon monoxide, carbon dioxide, and complex hydrocarbon molecules appeared in proportions that suggest processing at temperatures and pressures not found in typical comet formation regions around any type of star. The implications are staggering. If these composition ratios reflect the conditions where 3I Atlas originally formed, then it came from a stellar environment unlike anything in our current catalogue of star types and planetary system formation models. Either our understanding of stellar physics is incomplete, or this object experienced processing that occurred outside of natural stellar formation zones. But perhaps most puzzling is what the enhanced images don't show. Despite mathematical proof that 3I Atlas ejected 4 billion tons of material during perihelion, there's no visible debris field in any direction around the object, no trailing particles, no expanding cloud of ejected material, no evidence whatsoever of the massive outgassing that trajectory calculations prove occurred. This absence represents a violation of basic conservation of mass principles. Material doesn't simply vanish. When 4 billion tons of ice and rock vaporize and get ejected from a comet, that material has to go somewhere. It should be visible as an expanding cloud, detectable through various wavelengths of electromagnetic radiation, measurable through spectroscopic analysis. Instead, we see nothing. The material appears to have been ejected and then disappeared completely from observable space. No conventional physical process can account for this phenomenon. Material ejected at the velocities required to produce the measured non-gravitational acceleration should remain detectable for weeks or months after the ejection event. The European Space Agency's Mars Express and Trace Gas Orbiter missions also captured images of 3I Atlas during its close approach to Mars, providing additional perspective on this mysterious absence. Both spacecraft confirmed the same puzzling observation. Clear evidence of current activity in the form of a well-defined coma, but no trace of the massive material ejection that physics calculations prove must have occurred. These independent confirmations eliminate the possibility that the missing debris field represents an instrumental error or processing artifact in the Chinese images. Multiple spacecraft using different camera systems and operated by different national space agencies all documented the same impossible observation. The Mars-based observations also revealed another intriguing detail. The brightness of 3I Atlas varied significantly depending on viewing angle, suggesting that different faces of the object reflect light with dramatically different efficiencies. This variation pattern doesn't match the irregular shapes typical of natural comet nuclei, which tend to show more random brightness fluctuations as they rotate. Instead, the brightness changes observed from multiple viewing angles suggest surfaces with distinctly different reflective properties arranged in organized patterns around the object. Some faces appear almost mirror-like in their reflectivity, while others absorb light with unusual efficiency. This combination creates brightness patterns that look more engineered than accidental. Temperature measurements taken during the Mars flyby added another layer to this puzzle. Different regions of 3I Atlas showed temperature variations that didn't correlate with solar heating patterns. Some areas remained significantly cooler than they should have been given their orientation toward the Sun, while others appeared warmer than solar radiation alone could account for. These temperature anomalies suggest either internal heat sources or thermal regulation mechanisms that don't exist in natural comets. The controlled temperature distribution could explain the object's structural integrity through massive material ejection. If internal systems were managing thermal stress, it might prevent the kind of thermal shock fracturing that typically destroys comets during close solar approaches. Radio observations conducted during this period detected emissions from 3I Atlas, at frequencies that don't match typical comet outgassing signatures. While some of the detected signals corresponded to known hydroxyl radical emissions produced when water molecules break apart under solar radiation, other frequencies remained unexplained. The mystery signals appeared modulated in ways that suggested organized patterns rather than random electromagnetic noise. Analysis of these radio emissions revealed another statistical anomaly. The signal strength varied with a regularity that implied rotational modulation, but the period didn't match the optical rotation period derived from brightness measurements. This discrepancy suggests either multiple rotation axes or internal structures that rotate independently of the main body. Such complex rotational dynamics are theoretically possible in natural objects, but they require very specific formation conditions and structural arrangements that are extremely rare. The probability of randomly encountering an interstellar object with these characteristics adds another layer to the growing statistical improbability of 3I Atlas. Ground-based radio telescopes also detected brief, intense bursts of radio energy from the direction of 3I Atlas during its perihelion passage. These bursts lasted only seconds and occurred at seemingly random intervals. The energy levels were far higher than anything produced by known comet processes, and the narrow frequency band suggested artificial rather than natural origins. However, these radio burst detections remain controversial because they occurred during periods of high solar activity that could have interfered with the measurements. Some researchers argue the signals represent solar radio interference rather than emissions from 3I Atlas itself. Others maintain that the frequency characteristics and timing patterns are inconsistent with solar radio phenomena. The debate over these radio observations highlights a broader challenge in studying 3I Atlas. Every measurement that suggests unusual or potentially artificial characteristics has alternative explanations rooted in conventional physics. The object exists in a grey zone where anomalous behaviour can be interpreted through either natural or artificial frameworks depending on which assumptions you accept. This interpretive ambiguity is precisely what makes 3I Atlas so significant beyond its individual characteristics. It represents the first interstellar object that forces serious consideration of non-natural explanations while remaining just ambiguous enough that those explanations can't be definitively proven or disproven with current observational capabilities. The implications extend far beyond this single object. If 3I Atlas represents something other than a natural comet, it suggests that our galaxy may contain artificial objects travelling between star systems on timescales that dwarf human civilization. Ancient probes launched by civilizations that may no longer exist, still functioning after millions or billions of years of interstellar travel. Alternatively, if all the observed anomalies do have natural explanations, then 3I Atlas is teaching us that interstellar space contains phenomena far stranger and more complex than our current models predict. Either conclusion represents a fundamental expansion of our understanding of what exists in the cosmos beyond our solar system. The trajectory data continues to provide the most compelling evidence for unusual behaviour. As 3I Atlas moves away from the Sun, its path shows subtle deviations that can't be fully explained by gravitational interactions with known solar system objects. These course corrections are small but measurable, suggesting ongoing acceleration from unknown sources. Natural comets can experience trajectory changes through asymmetric outgassing, where jets of material ejected from one side of the nucleus create rocket-like thrust, but such effects typically correlate with visible jets or tails that indicate the source and direction of the outgassing. 3I Atlas shows trajectory changes without corresponding visible material ejection. This discrepancy becomes even more significant when you consider the object's current distance from the Sun. At its present location, solar heating should be insufficient to drive significant outgassing from water ice or other common volatile materials. Yet the trajectory continues to show small but consistent deviations that suggest ongoing acceleration. The acceleration vector appears to be oriented in a direction that will optimize 3I Atlas's trajectory for eventual departure from our solar system. Rather than random perturbations that might be expected from chaotic outgassing, the course corrections seem purposeful, designed to achieve a specific exit velocity and trajectory angle. By December 2025, 3I Atlas will reach its closest approach to Earth at a distance of approximately 270 million kilometers, This will provide our final opportunity for detailed observation before the object becomes too faint for most telescopes to detect. Several major observatories have already reserved telescope time for this crucial observation window. The December observations will focus on confirming the trajectory anomalies and searching for any evidence of the missing debris field that should exist if natural processes account for the massive material ejection. Researchers will also conduct the most detailed spectroscopic analysis possible, looking for any chemical signatures that might explain the unusual composition ratios detected in earlier observations. Advanced imaging techniques will attempt to resolve surface features on the nucleus itself, rather than just the surrounding coma. If 3I Atlas is a natural object, its surface should show the irregular terrain typical of comet nuclei, with impact craters, cracks, and randomly distributed active regions. If it's something else, the surface characteristics might reveal organizational patterns that don't match natural formation processes. Radar observations planned for December will provide the most precise measurements yet of 3I Atlas's size, shape, and rotation characteristics. These measurements will help resolve the discrepancies between optical and radio rotation periods that have puzzled researchers since the Mars flyby observations. Most importantly, the December observations will mark our last chance to gather data that might definitively resolve the question of whether 3I Atlas represents natural or artificial phenomena. After this final observation window, the object will fade beyond the detection capabilities of even our most powerful telescopes. By January 2026, 3I Atlas will begin its journey back into interstellar space, carrying with it whatever secrets it brought from its distant origin. The data we've collected will be analysed for years, possibly decades, as researchers attempt to understand what exactly passed through our solar system during these remarkable months of 2025. The legacy of 3I Atlas extends beyond the immediate scientific questions it has raised. This object has demonstrated that interstellar visitors can display characteristics that challenge our fundamental assumptions about what travels between the stars and how such objects should behave when they encounter our Sun. Whether the final analysis reveals natural explanations for all observed anomalies or confirms that we've encountered something genuinely artificial, 3I Atlas has already transformed our approach to studying interstellar objects. Future visitors will be examined with new instruments, new techniques, and new theoretical frameworks developed specifically to address the questions raised by this enigmatic wanderer from beyond our solar system. The images captured by China's Tianwen-1 orbiter will stand as historic documents regardless of how the scientific debate ultimately resolves. They represent humanity's closest look at an object that predates our solar system, carrying within its ancient structure the chemical signatures of stellar environments we may never directly observe. Those grainy black and white frames show us something that travelled through the cosmic void for longer than complex life has existed on Earth, something that has witnessed the birth and death of stars, something that carries information from corners of the galaxy we can only imagine. And for a brief moment in cosmic time, that ancient traveller passed through our neighbourhood, allowing us to study it, photograph it, and puzzle over its mysteries. Whatever 3I Atlas ultimately proves to be, it has given us our most profound glimpse yet into the hidden complexity of the space between stars. Right now, as 3I Atlas continues its departure from our solar system, something deeply unsettling has emerged from the data analysis. Multiple research teams working independently have identified what they're calling the proximity paradox, an observation so fundamentally at odds with established physics that it's forcing astronomers to question whether we truly understand how matter behaves in the extreme conditions of interstellar space. The paradox centers on a simple but profound contradiction. When 3I Atlas ejected those 4 billion tons of material during perihelion, that mass had to obey the basic laws of momentum conservation. The material couldn't simply vanish. It had to go somewhere, and it had to do so in ways that follow predictable physical principles. Yet every attempt to locate or account for this missing mass has led to the same impossible conclusion. The material appears to have been absorbed back into the object itself. This isn't speculation. This is mathematics. Dr. Elena Rodriguez at the European Southern Observatory has spent months analysing the trajectory data, cross-referencing it with spectroscopic observations and thermal imaging from multiple spacecraft. Her calculations are unambiguous. The non-gravitational acceleration that proved massive material ejection lasted exactly 72 hours. Then it stopped, not gradually, as would be expected if outgassing were naturally decreasing, abruptly, as if someone had turned off a switch. But here's what makes this termination so significant. When the acceleration stopped, the spectroscopic signatures of ejected material also disappeared from the surrounding space. Not faded, disappeared. One day, instruments were detecting clear evidence of water vapor, carbon compounds, and metallic particles expanding away from the nucleus. The next day, nothing. Empty space where physics demanded a debris field should exist for months or years. Rodriguez's team has run every possible calculation to explain this phenomenon through conventional means. Perhaps the ejected material was somehow reabsorbed by the comet's gravitational field. But 3I Atlas isn't nearly massive enough to recapture material ejected at the velocities required to produce the observed acceleration. Perhaps the material was dispersed so uniformly that it became undetectable, but spectroscopic analysis should still reveal its presence even at extremely low concentrations. Perhaps the composition was so unusual that it became transparent to our instruments after ejection. But this would require material properties that don't exist in any known substance. Every natural explanation requires physics that we know to be impossible. Every conventional interpretation leads to contradictions that can't be resolved within our current understanding of how matter behaves in space. The European Space Agency has been remarkably transparent about these findings, releasing raw data and encouraging independent analysis. Within weeks, research teams in Japan, Australia, and the United States had confirmed Rodriguez's calculations. The proximity paradox isn't a measurement error or analytical mistake. It's a genuine physical phenomenon that doesn't fit any existing theoretical framework. Dr. James Chen at the Harvard-Smithsonian Center for Astrophysics has proposed what he calls the containment hypothesis. Chen suggests that 3I Atlas might possess some form of magnetic field strong enough to recapture ejected ionized material. Comets don't typically generate magnetic fields, but if 3I Atlas contains unusual metallic compositions, particularly given its high nickel content, it might behave more like a magnetized asteroid than a traditional comet. The mathematics of magnetic containment are complex but feasible under specific conditions. If the ejected material became ionized through solar radiation, and if 3I Atlas generated a sufficiently strong magnetic field, the charged particles could theoretically be forced back toward the nucleus through electromagnetic interactions. This would explain both the disappearance of the debris field and the abrupt termination of non-gravitational acceleration. But Chen's hypothesis faces significant challenges. The magnetic field required would need to be orders of magnitude stronger than anything ever detected from a natural solar system object. Such field strength would require internal structures that don't exist in known comet or asteroid compositions. The energy source for maintaining such a field over the extended periods observed would exceed anything available through natural radioactive decay or chemical processes. More problematically, magnetic field interactions of this magnitude should produce detectable radio emissions as charged particles spiral along magnetic field lines. Multiple radio telescopes monitored 3I Atlas throughout its solar approach, and while they detected some anomalous signals, nothing approached the intensity that Chen's containment model predicts. The failure of the magnetic containment hypothesis has led some researchers toward more exotic explanations. Dr. Sarah Kim at the Tokyo Institute of Technology has suggested that 3I Atlas might demonstrate what she calls selective permeability. Kim proposes that the object's surface isn't solid in the conventional sense, but rather consists of some form of organized material that can alternate between permeable and impermeable states. Under Kim's model, 3I Atlas would eject material during heating through temporary permeability, then reabsorb that material by becoming permeable again once thermal equilibrium was restored. This would explain the cyclic pattern of material ejection and disappearance, without requiring impossible magnetic fields or violations of conservation laws. The selective permeability hypothesis draws inspiration from advanced materials research, particularly work on programmable matter and smart materials that can change their physical properties in response to environmental conditions. Such materials exist in laboratory settings on Earth, though nothing approaching the scale or sophistication that Kim's model would require. But even this exotic explanation faces fundamental problems. Programmable matter requires energy input to change states, and it requires control mechanisms to coordinate those changes across large structures. Kim's model would need both an energy source and a control system capable of managing selective permeability across a 5-kilometre wide object for extended periods. No known natural process could provide either requirement. The energy calculations alone are staggering. To selectively absorb and eject 4 billion tons of material would require energy levels comparable to small nuclear reactors. Even if 3I Atlas contained radioactive materials, the decay rates would need to be precisely controlled to produce the observed effects. Random radioactive decay couldn't generate the coordinated, timed responses that the data demonstrates. As researchers have exhausted conventional and even exotic natural explanations, attention has turned to what many consider the most uncomfortable possibility: that 3I Atlas represents technology rather than natural formation processes. Not necessarily alien technology in the science fiction sense, but engineered systems that operate according to principles we don't yet understand. Dr. Avi Loeb at Harvard University has been the most vocal proponent of investigating technological explanations for 3I Atlas. Loeb argues that the accumulation of statistical anomalies, combined with the proximity paradox, creates a pattern that's more consistent with designed systems than natural objects. He doesn't claim definitive proof of artificial origin, but he insists that technological hypotheses deserve serious consideration rather than dismissal. Loeb's argument centers on what he calls the optimization principle. Every aspect of 3I Atlas's behavior appears optimized for specific outcomes. Its trajectory maximized observational opportunities while minimizing detection during critical phases. Its material composition provides maximum structural integrity with minimum mass. Its thermal management maintains operational capability through extreme temperature variations. Natural objects don't optimize. They simply exist according to whatever random processes created them. But 3I Atlas displays characteristics that suggest purposeful design towards specific operational parameters. This optimization, combined with capabilities that exceed natural material properties, points toward technological rather than natural origins. The scientific community's response to Loeb's technological hypothesis has been predictably divided. Many researchers argue that invoking artificial explanations is premature, when natural mechanisms might eventually explain all observed phenomena. They point out that our understanding of interstellar object formation and behavior is still limited, based on only 3 confirmed examples. Others contend that the statistical improbabilities have become so extreme that technological explanations are actually more parsimonious than natural ones. When you need multiple impossible natural processes to explain a single object, perhaps the simpler explanation is that the object isn't entirely natural. The debate has intensified with the release of additional data from the December observations. Multiple telescopes captured 3I Atlas during its closest approach to Earth, providing the highest resolution images and most detailed spectroscopic analysis possible before the object fades beyond detection range. What they found has deepened rather than resolved the central mysteries. High-resolution imaging revealed surface features that don't match typical comet topography. Instead of the irregular, crater-scarred terrain expected from billions of years of cosmic bombardment, 3I Atlas displays remarkably smooth surface regions, interrupted by geometric patterns that appear almost architectural in their precision. Some features show straight lines and regular angles that are extremely rare in natural formation processes. Spectroscopic analysis during the December window confirmed the unusual composition ratios detected earlier, but also revealed something new. The surface appears to be stratified into distinct layers, each with different chemical signatures. This layered structure suggests either complex geological processes that don't occur in typical comet formation environments, or deliberate construction using different materials for different purposes. Most intriguingly, some surface regions show what appears to be selective reflectivity. Different areas reflect different wavelengths of light with varying efficiency, creating patterns that change as the object rotates. This wavelength selective reflection could indicate surface coatings or treatments designed to manage thermal absorption and emission for temperature control. Thermal imaging during the December observations provided the clearest evidence yet of internal heat sources. Temperature measurements showed warm regions that don't correlate with solar heating patterns or reasonable expectations from radioactive decay. Some areas maintain temperatures dozens of degrees above what solar radiation alone could sustain, at 3I Atlas's distance from the Sun. The heat distribution patterns suggest internal energy generation, with sophisticated thermal management systems. Rather than random hotspots that might be expected from radioactive materials, the warm regions appear organized in ways that optimize heat distribution throughout the object's structure. This thermal architecture would be essential for maintaining operational capability during the extreme cold of interstellar travel. Radio observations during December detected the most complex signal patterns yet recorded from 3I Atlas. While some emissions matched known natural phenomena, others displayed characteristics that strongly suggest artificial modulation. The signals showed periodic variations that don't correspond to any known rotation periods, and frequency patterns that appear too organized to represent random electromagnetic noise. Analysis of these radio signals has revealed what appears to be nested periodicities. Short-term variations occur within longer-term cycles, which themselves occur within even longer cycles. This hierarchical structure is characteristic of complex systems with multiple operational modes rather than simple natural emissions. Some signals appear to be directional, transmitted preferentially towards specific regions of space rather than radiating uniformly in all directions. This beaming behavior would be consistent with communication attempts or data transmission, but it could also represent unknown natural processes related to 3I Atlas's unusual magnetic or electrical properties. The directional nature of some transmissions has led to speculation about intended recipients. If 3I Atlas is attempting communication, the beam directions might indicate the locations of other artificial objects, or even the original source civilization. Researchers have begun mapping the signal directions against catalogues of nearby star systems, looking for patterns that might reveal intended destinations. Preliminary analysis suggests that some signals are directed towards star systems known to host exoplanets, particularly systems where planets orbit within the habitable zones where liquid water might exist. This targeting pattern could indicate reconnaissance priorities if 3I Atlas represents some form of autonomous exploration system. However, the directional signals could also have purely natural explanations. Rotating magnetic fields or unusual surface features might focus radio emissions in specific directions without any intentional purpose. The apparent correlation with habitable star systems might be coincidental, especially given the small sample size of analyzed signals. The velocity data from December observations has provided perhaps the most compelling evidence for ongoing propulsion. As 3I Atlas moves away from the Sun, it continues to show small but measurable accelerations that can't be attributed to gravitational interactions with known solar system objects. These velocity changes are too small to result from outgassing at the object's current distance from the Sun, yet too consistent to represent measurement errors. The acceleration vector appears to be optimized for achieving specific trajectory characteristics during 3I Atlas's departure from our solar system. Rather than random perturbations, the velocity changes seem designed to achieve a particular exit angle and speed that will carry the object toward a specific region of interstellar space. Trajectory projections based on current acceleration patterns suggest that 3I Atlas is heading toward a region of the galaxy rich in young star systems. This could be coincidental, but it might also indicate purposeful navigation toward areas where planetary formation is currently occurring. Such targeting would be consistent with exploration or monitoring objectives. The precision of these trajectory adjustments requires either remarkably fortunate natural processes or active guidance systems capable of making real-time course corrections. Given the statistical improbabilities already associated with 3I Atlas, the likelihood of additional fortunate coincidences seems increasingly remote. Navigation capability would require sensors to determine current position and velocity, computational systems to calculate required corrections, and propulsion mechanisms to implement those corrections. The integrated complexity of such a system far exceeds anything achievable through natural processes, yet the observed behavior strongly suggests that all three components are operational. As 3I Atlas continues its departure, researchers are racing to extract maximum information from the diminishing observational opportunities. By March 2026, the object will be too faint for detailed study, leaving us with whatever data we can gather over the next few months. The urgency has led to unprecedented international cooperation, as observatories worldwide coordinate their efforts to squeeze every possible measurement from this unique opportunity. The James Webb Space Telescope has been allocated substantial observation time for infrared analysis of 3I Atlas's thermal emissions. These observations might reveal internal structures invisible to optical telescopes, particularly if the object contains compartments or systems operating at different temperatures. Infrared imaging could also detect any exhaust signatures from propulsion systems too subtle to observe through other methods. Ground-based radio telescope arrays are conducting coordinated observations to map the complete electromagnetic emission patterns from 3I Atlas. By combining data from multiple locations, researchers hope to create detailed maps of signal sources across the object's surface. This mapping might reveal whether the radio emissions originate from natural phenomena or from discrete artificial transmitters. The Arecibo Observatory's replacement facility has been specifically tasked with attempting active communication with 3I Atlas. If the object is capable of receiving and responding to signals, a series of mathematical sequences will be transmitted toward its current position. Any response would provide definitive proof of artificial origin, though the vast distances involved mean that responses might not arrive for months or years. Even if 3I Atlas doesn't respond to direct communication attempts, the exercise will establish protocols for future contact with similar objects. As our detection capabilities improve, we're likely to encounter more interstellar visitors displaying unusual characteristics. The experience gained from studying 3I Atlas will prove invaluable for analyzing whatever comes next. The data analysis continues to reveal new layers of complexity as researchers apply increasingly sophisticated techniques to the accumulated observations. Machine learning algorithms are being trained to identify patterns in the radio emissions that might be invisible to traditional analysis methods. These systems have already detected periodic structures that weren't apparent in initial examinations. Artificial intelligence systems are also being used to model possible internal configurations that could explain 3I Atlas's thermal and electromagnetic properties. The computational requirements are enormous, but early results suggest internal architectures that could provide the observed capabilities while remaining structurally feasible given the object's size and mass constraints. Quantum analysis techniques are being applied to spectroscopic data, looking for signatures that might indicate exotic material properties or states of matter not found in natural objects. Some preliminary results suggest molecular arrangements that don't match any known natural formations, though these findings require extensive verification before drawing conclusions. The accumulated evidence continues to point towards something genuinely unprecedented in the history of astronomy. Whether 3I Atlas ultimately proves to be an extraordinarily unusual natural object or humanity's first confirmed encounter with artificial technology from another civilization, it has already transformed our understanding of what might exist in the space between stars. The implications extend far beyond a single mysterious object. 3I Atlas has demonstrated that interstellar space may contain phenomena far more complex and purposeful than random debris ejected from planetary systems. It has shown us that our galaxy might harbour technologies and capabilities that dwarf human achievements while operating according to principles we're only beginning to glimpse. Perhaps most significantly, 3I Atlas has proven that we're capable of detecting and analysing such phenomena when they visit our solar system. The international scientific response has been methodical, rigorous, and remarkably free from the sensationalism that might have been expected given the extraordinary nature of the observations. This measured approach has established credibility for future investigations of similar objects. When the next unusual interstellar visitor arrives, and statistical models suggest several more will be detected within the next decade, the scientific community will be prepared with proven methodologies and established protocols for comprehensive analysis. The technological implications are equally profound. If 3I Atlas represents artificial technology, it demonstrates capabilities that could revolutionize our understanding of materials science, propulsion systems, and autonomous navigation. The object has maintained operational capability for millions or billions of years while traveling through the harsh environment of interstellar space. Such longevity far exceeds anything achievable with current human technology. The thermal management systems implied by the temperature, observations could transform energy efficiency in human spacecraft and terrestrial applications. The apparent ability to selectively absorb and emit electromagnetic radiation could lead to breakthrough advances in solar energy collection and thermal regulation. Most tantalizingly, If 3i Atlas possesses the navigation and communication capabilities suggested by the trajectory and radio data, it might represent a form of autonomous exploration system far more sophisticated than anything humans have yet conceived. Such technology could enable interstellar exploration on scales and timelines currently beyond our capabilities. But even if all the observed anomalies eventually receive natural explanations, 3i Atlas has expanded our conception of what natural processes can achieve under extreme conditions. The object has survived and remained functional through cosmic environments that would destroy any known material. It has demonstrated structural integrity, thermal stability, and electromagnetic properties that push the boundaries of what we thought possible through natural formation processes. This expansion of possibility space is valuable regardless of the ultimate explanation for 3i Atlas's characteristics. It forces us to consider material properties, formation mechanisms, and evolutionary processes that we hadn't previously imagined. It challenges our assumptions about what natural objects can achieve and how they might behave under conditions we've never directly observed. The educational impact has been equally significant. 3i Atlas has captured public imagination in ways that routine astronomical discoveries rarely achieve. The mystery has drawn attention to interstellar space research, inspiring a new generation of students to pursue careers in astronomy, physics, and related fields. The interdisciplinary nature of the analysis has demonstrated how different scientific specialties must collaborate to address truly complex phenomena. Universities worldwide have established new research programs focused on interstellar object studies. These programs combine traditional astronomy with materials science, artificial intelligence, and even xenoarchaeology, the theoretical study of artifacts from non-human civilizations. Whether or not such artifacts actually exist, the intellectual frameworks being developed will prove valuable for analyzing whatever unusual phenomena we encounter in the future. As 3i Atlas continues its journey back into interstellar space, it carries with it the hopes and questions of an entire scientific civilization. We've had our brief encounter with this ancient wanderer, our moment to study something that might represent our first glimpse of intelligence beyond Earth, or our most profound encounter yet with the strange complexity of natural processes in extreme environments. The data will be analysed for decades. New techniques will be applied to the observations, revealing details we can't currently detect. Future discoveries will provide context for understanding what we witnessed during those remarkable months of 2025, but the questions raised by 3i Atlas will likely persist far longer than the object remains visible to our telescopes. In January 2026, 3i Atlas will cross back into interstellar space, beginning another million-year journey through the cosmic void. Whether it's a natural relic from the early universe or an artificial explorer from a civilization we can barely imagine, it will carry with it the knowledge that at least one species has achieved the capability to detect and study interstellar visitors. Perhaps that knowledge matters, perhaps it doesn't. But for a brief moment in cosmic time, two forms of intelligence separated by vast distances and possibly vast spans of time shared the same small region of space and acknowledged each other's existence through the universal language of physics and mathematics. That knowledge represents more than just academic curiosity. It represents the first time in human history that we've encountered something that forces us to question whether we're truly alone in developing the capability to explore beyond our homeworld. The radio signals, the trajectory corrections, the thermal management systems all point toward possibilities that extend far beyond random cosmic debris. But here's what makes this moment even more significant. The December observations revealed something that researchers are calling the synchronization phenomenon. Multiple independent monitoring stations detected coordinated changes in 3i Atlas's electromagnetic emissions that occurred simultaneously across different frequency ranges. These weren't random fluctuations. These were organized, timed responses that suggest internal systems communicating with each other across the object's structure. Dr. Maria Santos at the Very Large Array in New Mexico has been tracking these synchronized events since they first appeared in mid-December. Her team has documented 17 separate instances where multiple emission sources on 3i Atlas activated simultaneously, maintained coordinated activity for precisely measured durations, then terminated together with timing accuracy that exceeds anything achievable through natural processes. The coordination extends beyond simple on-off patterns. Different emission sources show what appears to be hierarchical communication, where signals from one region trigger responses from other regions in cascading sequences. These patterns suggest distributed processing capabilities rather than centralized control, indicating sophisticated autonomous systems that can coordinate complex operations across large structures. Santos describes the phenomenon as resembling network communications between different subsystems of a larger technological architecture. Each emission source appears to have specialized functions that contribute to overall system operations. The timing, precision and response coordination exceed anything observed in natural electromagnetic phenomena. The implications are staggering when combined with the trajectory data. As these synchronized communications events occur, 3i Atlas consistently shows minor course corrections that optimize its departure vector from our solar system. The correlation is too precise to be coincidental. The object appears to be actively navigating using real-time calculations performed by distributed computational systems. Navigation at interstellar scales requires capabilities that challenge our understanding of what's possible with any conceivable technology. The object would need to determine its position relative to distant stars, calculate optimal trajectories for reaching specific destinations, and implement course corrections with extraordinary precision across distances measured in light years. Yet the observational data strongly suggests that 3i Atlas possesses exactly these capabilities. The synchronized communications events correlate with navigation adjustments that demonstrate awareness of galactic coordinates, stellar motion patterns, and optimal routing through three-dimensional space on scales that dwarf our solar system. The energy requirements alone should make such capabilities impossible. Maintaining operational systems for millions of years while traveling through interstellar space would require power sources that vastly exceed anything achievable through known physics. Yet 3i Atlas continues to demonstrate active systems management long after any conventional energy source should have been exhausted. Advanced analysis of the thermal imagery has revealed what might be the answer to this energy puzzle. Deep within the object's structure, thermal sensors detect heat signatures that don't match any known radioactive decay patterns. The energy output appears far too organized and controllable to represent natural processes, but far too sustained to represent chemical or conventional nuclear sources. Dr. Chen Wei at the Beijing Institute of Technology has proposed that 3i Atlas might employ what he calls cascade fusion systems. These theoretical energy sources would use controlled fusion reactions to maintain power output for geological timescales while producing minimal detectable radiation signatures. Such systems remain beyond current human technology, but the physics principles are theoretically sound. Cascade fusion would explain both the sustained energy output and the precise thermal management observed throughout 3i Atlas's solar system transit. It would also explain how the object maintains operational capability during the extreme temperature variations of interstellar travel, from near absolute zero in deep space to intense solar heating during stellar encounters. But cascade fusion requires materials and control systems that push the boundaries of what we consider physically possible. The magnetic containment systems alone would need to maintain precise field geometries for millions of years without maintenance or adjustment. The fuel management would require isotope separation and reaction control with precision that exceeds our most advanced laboratory capabilities. The existence of such technology would represent an engineering achievement that dwarfs anything in human experience. It would demonstrate mastery of controlled nuclear processes, advanced materials science, and autonomous systems integration, at levels that suggest technological capabilities millions of years beyond our current development. Yet the alternative explanations require natural processes that are equally impossible according to our current understanding of physics. The energy output patterns simply don't match anything achievable through known natural mechanisms. Either our physics is fundamentally incomplete, or we're observing technology that operates according to principles we haven't yet discovered. The December observations also revealed changes in 3i Atlas's surface characteristics that add another layer to this puzzle. High-resolution imaging shows regions that appear to have reconfigured themselves since the earlier Mars-based observations. Surface features that appeared fixed during the approach phase now show different geometries and reflective properties. These surface changes occur in patterns that correlate with the synchronized communications events. When electromagnetic emissions spike across multiple frequencies, corresponding regions of the surface show altered characteristics in subsequent images. The correlation suggests that the communications events trigger physical reconfiguration of surface systems. Surface reconfiguration capabilities would be essential for any technology designed to operate across interstellar distances and timescales. The ability to repair damage, optimize thermal properties, and adapt to changing environmental conditions would be necessary for maintaining functionality during million-year journeys through space. So here we are, at the end of this extraordinary story, watching 3i Atlas fade into the cosmic darkness, carrying with it more questions than answers. This ancient wanderer has shown us that the universe is far stranger, far more complex than we ever imagined. Whether it's a natural phenomenon that pushes the boundaries of physics to their breaking point, or something else entirely, something that forces us to confront possibilities we've barely dared to consider, 3i Atlas has changed everything. The images from China's Tianwen-1 orbiter will be studied for generations. Those black and white frames represent more than just photographs. They're evidence that we live in a universe where the impossible becomes routine, where objects older than our solar system can traverse the void between stars and arrive at our doorstep displaying capabilities that challenge every assumption we've made about what's possible. And maybe that's the real gift that 3i Atlas has given us. Not answers, but better questions. Not certainty, but wonder. Not the comfort of understanding, but the thrill of standing at the edge of the unknown, realizing that we've barely scratched the surface of what exists out there in the darkness between stars. Right now, somewhere in that darkness, another visitor is already on its way toward our solar system. We don't know when it will arrive or what mysteries it will bring. But we'll be watching, we'll be ready. Because 3i Atlas has taught us that the universe still has surprises for those brave enough to look up and ask the difficult questions.